All right, this is significant figures part number 3. And this one we're going to look at rounding off answers when you actually do measurements. Now, if you were in a math class and you had to do some math problems and you have to round off answers, you probably go, "Hey, Mr. Madziar, where do you want these rounded off?" And Mr. Madziar would be like, "Oh, yeah, round them off to a whole number." All right, so he'll tell you where to round them off. When you're in a science class, what I'm going to do is when you ask me, "Mr. Babe, where am I supposed to round off these answers?" I'm going to tell you, figure it out. What do I mean by figure it out? It means you got to utilize the stuff that we talked about in the last 2 videos about accuracy and precision and the idea of significant figures in order to know where you can round these measurements off at. And that's what that rule letter F is in your notes when you're rounding off an answer. When you are adding or subtracting numbers, then it says round off the answer to no more digits to the right of the decimal than measurements with the least number of digits to the right of the decimal. Oh my word, what did that say? Well, let's look at what this means. Well, let's take this and we're going to go 2 plus 3.57. So if I add those 2 measurements together, I'm going to get something like, let's see, that's what, 5.57. All right. So this was 2 measurements that we had, and you added them together. Now, what I want to do is I want to find out where am I supposed to round this thing off. Well, we can use these 2 measurements that you measured to decide where this thing's supposed to round off. And what it is we're looking at who was accurate and who wasn't in this measurement. Well, this guy down here was really accurate because he really measured the thing out. It wasn't just 3 meters long. It was 3.57. It was a little bit more than another half a meter beyond 3. It was 3.57. This guy up here, he said, "Yeah, well, it was about 2. Got her." Yep. Was it really 2? Was it 2.2? Was it 2.4? Maybe it was 1.5. Maybe it was 1.5. And he was like, "Yeah, well, pretty much 2. So who kind of messes up this measurement down at the bottom? This guy right up here. Right? Now, what we do in science is we look at, because it's addition or subtraction, you look at how many digits there are to the right of the decimal. So right of the decimal, that means we're decimal, and for this guy is right here. How many digits are over here to the right? None. So I'm going to put a little 0 up here. So I know there are none to the right of the decimal in that 2. How many digits to the right of the decimal are in this 3.57? Well, there's the decimal. 1, 2. So this guy's got 2 to the right of the decimal. So which measurement gives me the least number of digits to the right of the decimal? The 2. He has none. So according to this rule, then my answer can have none to the right of the decimal. So that means here's my decimal, so I got to round off to this spot by looking at that 5. So this number is going to round off to, that's what the little quick squiggly line is there, means approximately rounds off to. It's going to round off because that's 5 or greater, bounces this up, and it becomes 6 is the right answer. So that's where you'd round this thing off because it was addition or subtraction. All right, and all it is again is you're looking at number of digits to the right of the decimal. Now let's go to the second rule. What if we multiply or divide? Let's try another one. Multiplying or dividing. So let's go 4.73 multiplied by 2. All right. So if I multiply this thing out, I'm going to get what? 6, it's 14, 1, that's 9. So 9.46. All right, make sure you can see that. 9.46. Now where do I round this guy off at? Well, this time now I'm looking at significant figures. Oh gosh, now I got to think back to those rules in the previous video. Now, this is not digits to the right of the decimal. How many significant figures does this guy have? 1, 2, 3. So he has, I'm going to put a little 3 here just so I can remember. He's got 3 significant figures. How many significant figures does this guy got? 1. He's only got 1 significant figure. According to that second rule, when you multiply or divide, round the answer off to have no more significant figures than the measurement with the least number of significant figures. Which one of these guys has the least number of significant figures? This one, because he's only got 1. My answer can only have 1 significant figure. So my first significant figure is this guy, the 9. So I'm going to round off the 9 by looking at the 4. So when I round this guy off, if I round it off, it's going to round off to 9 is the right answer. Now notice that, look what ended up happening in this, we really had 9.46. But because this measurement was so not accurate, it was not measured out and being really accurate, trying to find that exact measurement it was, it really messes up my answer. my answer is I've got to round it off and get rid of 0.46. Another way of looking at this would be like you go to the store to buy something, and the guy's supposed to give you back $9.46, and he gives you $9 back. So there we go, we're good. See ya, have a good day. You know, wait, where's my 46 cents? You know, well, it's pretty close. It's 9.46, so I just give you $9 back. And you know, gosh, I want my 46 cents. That's what, again, where the significant figure thing comes in is we need to count in significant figures, right? Because then I would get my 46 cents back also, right? So again, that second rule, multiply or divide, round the answer off. So it has no more significant figures than the measurement with the least number of significant figures. All right, last little bit of this is percent error. And if you look at your notes, you add down percent error is error, and then it's got two lines on each side of it. That is the absolute value for error, and then divided by the accepted value times 100%. All right. To do an example of this, sorry, let me get my paper out. You're going to boil water in the lab. When you do it, you find out that the water boils at 99.1 degrees Celsius. Now, what's the correct temperature that water is supposed to boil at? It's supposed to boil at 100.0 degrees Celsius. So this is that's my measured value, right? That's my experimental one. That's my accepted value. So what we're going to do is we're going to put this stuff into the equation I just gave you, which was percent error equals, it is the accepted minus the experimental value, and we're going to take the absolute value of that. Absolute value means it's neither positive or it's always going to be positive. So if it's negative, you change it back to positive. And then we're going to divide that by the I made a mistake, accepted value. And we're multiply that by 100%. Okay, get my head out of the way. So we put stuff into this. We're looking percent error.
Teachers, the network is back up.
Sorry, as you can tell, I'm doing this at school. But so I'm going to take my accepted value, which is 100.0, minus the experimental, which is 99.1. Take the absolute value of that, divide that by the accepted value, which is 100.0, and multiply that by 100%. So if I do the math on this, if I subtract that, I'm going to get this to be 0.9 divided by 100.0 times 100%. And if you multiply this thing out, you'll get an answer of 0.900% error. Now, what does that mean? That means my thermometer that I used, it didn't give me 100.0 like it was supposed to. It gave me 99.1. That's off a little bit. How much is it off by? 0.9%. It's a little bit off, right? But it is off. It's not accurate. It's not close to the right answer, right? And it's always going to be, what this tells me is this thermometer is always going to be off by 0.9% of what's the right answer every single time. So I'm really like, man, I should probably find a thermometer that's going to be 100% accurate or a whole lot closer to 0% error. I don't want any error on this. All right, with that concludes the notes concerning significant figures and the material related to that. So have a good day. We'll see you.